Welcome, everyone. Thank you for joining us today. My name is Natalia Martin, and I'll be a moderator for this webinar. Our topic for today is remoting into renewables. We're going to discuss the latest guidelines, including CISA, CCCS, and others, for secure remote access when it comes to renewables generation. Our panelists are Andrew Ginter, VP of Industrial Security at Waterfall Security Solutions, and Leo Franco, who is a co-founder and CEO. A couple of notes before we start. This webinar is being recorded. You will all receive an email with a link to the recording within a few days. There will be a Q&A session at the end of the webinar. Please make sure you submit your question in a Q&A panel at the bottom of your screen, and you can do it at any time during this session. We will try to answer all of your questions, but in case we're running out of time, we'll make sure to follow up with you individually and answer it via email. Also, one more thing I'd like to mention, if you have any questions about Waterfall Solutions in general and would like to speak to one of our experts, I'm going to share a link, a special link in the chat box for your convenience, so you can contact us directly. And with that, Andrew, the mic is yours.
Okay. Thank you, Natalia, and hello, everyone, and welcome to the webinar. Hello, Lior. Thank you for joining us. Our topic is remote access, especially for renewable generation. Renewable generation is the future of generation, and everybody's talking about remote access. We're going to talk about the latest guidance. We're going to talk about the security of remote access. And I wanted to say a word, one of the reasons that we invited Lior to this webinar is that he's not just the CEO and co-founder of Waterfall. He is also inventor or co-inventor of some of the technologies that we're going to be talking about. So let's begin. Let's talk about the problem. We're talking renewables, primarily wind and solar. In the world of wind generation, what are we talking about? You might look at one of these massive windmills and say it's a windmill. These things are big. They are, to a degree, infinitely adjustable. Okay, the blade angle changes. The device rotates. It's not just that the wind, forces the rotation to an optimal point for power generation. The orientation of the device is controlled to optimize power generation. When there's oscillation, the wind is oscillating, the tower is moving, things are changing. There's code in there. There's dynamic compensation for the oscillation to keep things steady, to keep maximum power being produced. And all of these things, we're talking about very large stuff that is moving, that is changing, that is adjusting constantly to match what's happening with the wind. These are all moving parts. Friction is the enemy of moving parts. Wear is, the consequence of friction. Vibration is a symptom of friction. And so what we have in these large, more complicated than they look devices, we have a lot of monitoring. We have active control to try and maximize the life of the device and maximize the power that it produces over the life of the device. The remote access equation here. I mean, with a conventional turbine, think a steam turbine in old school power plant, or think a gas turbine in a natural gas power plant. With conventional turbines, they also rotate. They also wear out. An average turbine, the manufacturer, the world's expert on the turbine, will remote into the turbine. Typically, they monitor these things 24/7. They remote in maybe once a quarter, maybe twice a quarter, to say, look, I've got some vibration problems building up. I got a hotspot anomaly in my gas turbine, I'm going to adjust things just a little bit to maximize the life of the turbine between services, to minimize services, to control maintenance. This is called predictive maintenance. Here's the problem. Wind turbines, every one of them wears out just as fast as a massive steam turbine. They're rotating. They wear, in a sense, at the same rate. A technician needs to log into, the turbine once a quarter, maybe twice a quarter, to adjust things so that you maximize the life. The problem is that in a large power plant, you might have 6 turbines. And so you've got 6 or 10 remote access sessions per quarter. With a wind farm, we've got a large wind farm, it's got 300 turbines. Every one of these maintenance sessions, remote sessions, takes an hour. We're talking 300, 400, 450 hours of remote access into the wind farm, adjusting these turbines every quarter. And the problem is that the turbine technology is not as mature as steam and gas turbines. There tends to be one vendor adjusting the steam and gas turbines. It's been around for 50 years. It's all integrated. Everybody knows how it works. With these devices, I mean, this was a couple of years ago. I had an owner and operator of a large wind farm talking to me saying, Andrew, it's not one vendor has to come into each of these 300 turbines once or twice a quarter. We've got 5 and 6 vendors coming into these things. The technology is just not as mature. There's many kinds of vendors involved. Every one of them is adjusting a different thing. The yaw control, the pitch control, the turbine. So we've got 5 and 6 vendors. If we've got 6 vendors coming in once per quarter to 300 turbines, do the math, that's 1,800 hours of remote access per quarter. There's only 500 working hours, 520 working hours in the average quarter. We're talking 2 and 3 and 4 remote access sessions every hour of every working day. Every hour, a different bunch of vendors logging into a different bunch of turbines to adjust a different bunch of parameters on those turbines. Remote access is important for conventional generation to manage the devices. It's unavoidable in a wind farm.
Yeah, Andrew, first of all, exciting stuff and happy to be here with you. It's not just the vendors. I mean, first of all, these renewable sites were built from the get-go to be remotely managed. I mean, nobody, or I hope so, has his office in a wind farm. Nobody wakes up in the morning and takes a bus to a solar plant. It's not what you do. So it's also the employees and the people that work in the company that operates these renewable plants. And as we saw through COVID, even that doesn't work all the time. I mean, sometimes you have issues with people getting in, or it's too costly, or there are other, it doesn't even need to be a pandemic. It could be weather issues. It could, you can't, especially in these types of facilities, you can't not have remote access capabilities. It's just intrinsically baked in everything that's part of that business.
There you go. So let's look at the other sort of big renewable out there, solar. What does a grid scale, grid style solar farm look like? We're talking, maybe 20, 30, on the outside, 75 megawatts, whereas a large conventional power plant is 750 megawatts, is 1,500 megawatts. The biggest one I visited was 4 gigawatts, 4,000 megawatts. So we're talking, by grid standards, comparatively small installations. Now, each of these installations, is still solar panels as far as the eye can see. That's the nature of a 20, 30 megawatt solar farm. So there's a lot of them. They tend to be smaller. And you might say, well, they're solar panels. They're sitting there. what kind of maintenance do they need? What kind of remote anything do they need? Well, if you talk to, again, owners and operators, many of the most efficient farms have the panels tracking the sun. They turn so that you maximize production. These are motors. These are moving parts. They wear out. They need to be repaired. They need to be diagnosed so that you know when to repair them and what parts of them to repair, because different parts can wear out. You can have dust, you can have, I don't know, in my geography, snow build up on these wretched panels. And so there's robots and machines that clean these things, which themselves need maintenance, if something isn't working, they need first to be diagnosed. Which of the 803 moving parts need to be replaced, or the entire unit needs to be replaced. There are drones that overfly these things because the panels themselves, you might say it's a panel. It's solid state. It lives forever. It doesn't. The panels can have defects. The panels can develop defects over time. The drones fly over these things looking for hotspots, looking for, there's instrumentation that's diagnosing which parts of the panel are working, which parts aren't working. Do I have, hotspots, meaning part of the panel has burned out and that panel needs to be replaced. These drones, again, moving parts. The intelligence in a solar installation tends to be in the inverter. This is a large device or several large devices, sometimes in series, sometimes in parallel. But what comes off the solar panels is direct current, DC. Varies between 350 and 950 volts DC, depending on the manufacturer, depending on the nature of the panel. The inverters convert that, pick a number, 350 volt DC to alternating current, and then feed it into a small substation, a transformer, to increase the voltage to a level that can be transmitted efficiently long distances, because these farms are all far away. There's not that many farms that are right next to the load, right next to the cities. And so these inverters are converting, they are tracking the sine wave of the grid. They are, emergency devices as well. If they discover problems with the flow of power or instability in the grid, they will disconnect. This is a big deal right now, sort of a side conversation. NERC has just put new rules in place for North America because a whole bunch of solar farms dropped out all at the same time because they all had exactly the same setting. A too sensitive setting. They detected the smallest variation in the grid and said, "Oh, help, help, there's a variation in the grid." And they all dropped out and the grid went, "What? We just lost a gigabyte of power." So these are complicated systems. There is, maintenance, there's remote access, there's vendors logging in, and because they're so small, there's not a 24/7 operator at each of these things. The standard, the commonplace practice is that most of these smaller farms, and there's hundreds of them in a typical power company, most of them are operated remotely. The operator's in another city. Their operator is remoting in. So remoteness, again, is intrinsic in this industry as well as in wind generation. And so the question becomes, okay, we have to do remote stuff. Why are we talking about that? Is that a problem? Well, whenever we have information moving across a wide area network, it might be the internet, it might be a leased line. The information's leaving the boundaries of our control room. It's leaving the boundaries of the physical site, the wind farm, the solar farm. It's traveling across the world. It's possible to intercept this stuff and tamper with it. Well, that's a cyber attack. What's the worst that can happen? Well, there's the obvious. Things can go down. There's less obvious. A lot of people don't consider the possibility of equipment damage. Well, what can you damage in a solar farm? You can utterly destroy the inverter if you operate it incorrectly. Instead of converting, instead of saying I'm converting, 350 volts to 120 DC or AC rather, you put a different equation. Say that, tell the inverter that, because these inverters, they work in Europe, they work in North America, they're configurable. Configure the inverter to produce 50 hertz instead of 60 hertz. The inverter takes 20 megawatts of power and argues with the grid. The inverter always loses. What's the symptom of losing the argument? Heat. The inverter has a built-in overheat, a heat sensor. If it gets too hot, it turns off the power. Tamper with the software, you tamper with the heat sensor, the inverter bursts into flames. Now the site is down until we can get a new inverter or 6. We have, and that's sort of consequence. Sorry. There's also the risk of, how would people get in? How do you bring about that consequence? You can steal credentials. You can exploit vulnerabilities in the internet exposed facilities that are remote control, remote access. The very latest attacks out there, and I don't have a threat briefing here, but if you're interested, have a look at the latest waterfall threat report. It's waterfall-security.com/2025-threat-report. The latest that everyone's talking about is living off the land. What does that mean? The bad guys get in, and instead of putting a piece of malware on the system and operating our infrastructure by remotely, maliciously using the malware, they get in through whatever means. They erase all trace of them getting in. They compromise an Active Directory controller or something, or steal credentials. Sometimes they just create new credentials for themselves. And now they log in every couple of days like a normal user. We have, 75 people logging into the wind farm every day. Well, now there's 76. Is anyone going to notice another user that logs in every once in a while and looks around and does user type things? These people use the operating system to attack the OT network. They don't have malware anymore. You run an antivirus on these systems and it comes up absolutely squeaky clean. There is no malware on there. This is the modern attack. These are all, things that we worry about, saying, well, I've exposed my OT system to this kind of thing coming in at me from the internet. Okay, now I'm worried. This is why we worry about remote access. Surveys show a lot of people are worried about remote access.
Andrew, I think you're jumping ahead. I mean, of course, all of these risks are here because of remote access and a few more. But there's some more basic risks that, remote access technologies, they require firewalls to get in and out from these remote sites that they remote into, these renewable site networks. And having a firewall there opens up a whole new list of risks that we all know about. This is why we founded Waterfall back in the days, because firewalls are not the right fit to sit in between an OT environment and the industrial control network and the internet, because of all of the consequences that you listed before. So the fact is, using remote access, you get all of the risks that you just listed, and on top of that, you get all of the other risks which are related to having a firewall, having it misconfigured. The firewall has 0 days, has vulnerabilities, etc., etc. And people can, bad people or systems can get in through the firewall, not through the remote access. You won't even notice that monitoring the remote access activity or trying to figure out what went wrong through the remote access, because they'll sneak in through the underlying firewall. So it's I think a multifold of risks and things to be concerned about when trying to figure out how to remote in, how to provide a good remote access solution to renewable networks.
I agree. I agree. If people are interested, we're not going to go into detail here, but there's also a report that Waterfall came out with recently called 13 Ways to Break a Firewall. We do need to understand the limitations of the technology we deploy. Just to give you one example, what's the low-tech way through a firewall? People might say, it's a firewall. You can't get through a firewall. Steal the admin password. Phish it. Add a rule that says allow all. Yeah. Will the help desk ever get a trouble report saying, I think the firewall's misconfigured. It's letting my stuff through. You don't get reports like that. You get reports when firewall doesn't let you through. So the bad guys get in, they add an allow all rule, and the help desk reports about, complaints about firewalls stop. The help desk is happy, and the bad guys are in. So, lots of other ways in the report if you're interested. But yeah, I take your point. So we have stuff to worry about. What are we going to do about it? Well, let's look at conventional solutions. I'm going to go through an attack scenario. Why? Because the way, we're going to talk about hardware enforced remote access. We're going to talk about the latest advice from governments. But the way that we compare the strength of security for two security postures, for two different designs, is attacks. You look at what attacks does one posture defeat with a high degree of confidence that the other one does not. So you have to understand, we have to evaluate attacks in order to compare security postures. Here's an architecture. We're talking about renewables. Let's pick wind. Back of the envelope, let's dumb it down, keep it simple. We've got a remote laptop, my laptop in a hotel room. You and I know it could be the vendor sitting in their office. It could be, an operator operating a solar farm. We've got my computer on the other side of the internet. We've got something in between. We all know it could be an IT network. It could be a leased line. But for the sake of argument, let's just say it's the internet. Keep it simple. I've got a laptop in my hotel room going across the internet. How do I get into the farm if I need to do some work there? I go in through a software remote access server. Okay, it might be a VPN firewall. It might be something fancier that with zero trust built in, but it's a computer running software. I connect to that computer running software, and I'm in. This is how it works into the wind farm, the target that we're trying to protect. So let's consider an attack scenario so we can use this attack scenario throughout the rest of the discussion here. This is actually in 2022. Chinese intelligence is accused of discovering a 0-day in Fortinet VPN servers and taking over 20,000 of them, internet-facing Fortinet VPN servers. Don't get me wrong, I'm not criticizing Fortinet. I actually like the Fortinet firewalls. But this happened. It was disclosed in 2024, but it actually happened in 2022. And what did they do? The classic attack is they used the compromised device to reach into the OT network. They pivoted. When you use a compromised device to attack other devices, it's called pivoting. Pivoting is the modern, sophisticated attack. Ransomware does it, nation states do it, intelligence agencies do it, activists do it if they can pull it off. This is the classic attack. And in a real sense, the attack is not surprising. All software has bugs. Some bugs are vulnerabilities. Some vulnerabilities we know about and we're madly trying to patch. Some of them are 0 days and we don't know about them, and our enemies are using them against us without our knowledge. But whenever we have one of these remote access points, one of the reasons these remote access things are, that we all worry about them so much is that in a real sense, these remote access systems are sitting ducks. They're on the IT network with a fixed IP address. They're on the internet with a fixed IP address. Any fool can connect to them and say, what version of software do you have? Oh, you're the latest. Well, why don't I just wait a little while? Look at the vendor. Oh, the vendor a minute ago published a new security update. Have you applied it yet? No. Let me go to the vendor website, look at the documentation, go to the CVE report. Oh, look, there's a proof of concept exploit in there. Tell my AI, take this, build it into my attack tool, and I'm through. I got into your firewall, I got into your software remote access system before you had a chance to patch the wretched thing. This is the world we live in. This is why, oh, where are we here? There we go. We promised to talk about the latest advice. This is the latest advice for OT remote access that came out from a combination of different national security agencies. I believe this was CISA in the US, FBI in the US, the Canadian government, the CCCS, and two different authorities in New Zealand, the New Zealand CERT and the New Zealand Government Communications Security Bureau. It's a goofy name. If you want to Google this, Google modern approaches to network access security. Really, they're talking about remote access, but they called network access security. And what do? They say, please, 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 people, stop using VPNs, stop using jump hosts. In part because they're software, in part because, VPNs have a whole different class of problems we haven't even talked about. But, one of the things about a VPN is that, it depends on the VPN. But a lot of VPNs, when I connect my laptop in the hotel room to the wind farm through a VPN, it is as if I walked up to the wind farm control system with a wire, plugged my computer into the control system. It's a virtual private network. It's a virtual connection to the private network. What does that mean? Well, it means when I'm there, physically plugged into the switch, which of the computers in the OT network can I connect to? Anyone. I'm on the switch. I can connect whatever I want. The VPNs, a lot of them, will give me that same experience. Meaning, if there's a piece of malware on my laptop, because I was connected to the internet 5 minutes earlier reading the news and clicked on something bad, there's a piece of malware on my laptop looking around saying, you're fully patched. There's nothing I can do here. And it sees the connection to the OT network and says, what's over there? Sends a couple of messages and goes, bonanza! There's 700 machines in there that have not been patched, and it goes wild through the VPN connection. This is another reason the authorities are saying, please, please, please stop using VPNs, stop using jump hosts, use something stronger. What are they recommending? On IT networks, they're saying, look, half of your IT users are remote anyway. They live in the cloud. You should be using these cloud-based facilities for managing remote access, for managing all of the security for your remote workforce. And they say, and if you're dealing with high consequence OT networks, critical infrastructures, you should be using hardware enforced unidirectional remote access. That's the latest advice. Really? What is that? Well, we're going to get into that. Leo, did you want to add anything here before I move on?
No, mainly, we've talked about this many times in different venues. It's very encouraging to see regulators catching up and being so direct about this. They, in other cases, don't tend to do it. Remote access, especially VPNs, but remote access in general is super dangerous and should be dealt in a very serious and open-eyed type of approach, because you are, as you said, you are letting somebody sit in on a computer inside your control network. You just don't think about it, but that's what you're letting them do. So once you assume that, all the rest becomes easier. Okay, now I understand the risks. Okay, somebody can sit in on that computer and do bad things. Who's sitting on that computer? I don't know. Stuff like that. So this is a very encouraging piece of work by regulators, and it's also nice to see that they are collaborating together. Hope to see more like this in the future.
There we go. So, CISA has recommended hardware-enforced unidirectional remote access. What is that? It's something new in the world, okay? It's a comparatively new technology. Lior is one of the inventors. His name's on the patent. What is it? There is software involved, but there's also hardware involved. It is designed to, minimize the attack surface. It's designed specifically to interrupt the pivoting path through the internet into the IT network, into the OT network, into the PLCs, interrupt that pivoting path, interrupt the attack avenue that sophisticated or even moderately sophisticated attacks use nowadays. So what is it? Well, it's based on unidirectional gateway technology. So we have to understand what is the unidirectional gateway. I'm going to touch that very briefly here. And then I'm going to come back to how do these things cooperate to do remote access, to do what feels like normal interactive remote access. The gateway, the NIST 882 standard defines it as a combination of hardware and software. The hardware is physically able to send information in only one direction. I mean, under the hood, if you look at the waterfall version of this product, if you lift the lid, an auditor can run their finger down that divider on the middle of the device, and they can verify visually that there's no cross connect inside the device. Really, it's two devices in one. Okay. They even have separate power, dual hot swap power supplies on each side. Nothing is shared across the two circuit boards. And the other thing I want to point out, look closely at the circuit boards. There's a big fat heat sink on the bottom of each of the circuit boards. That's a CPU. There's memory beside it. There is software that's part of the solution. That is how you animate the software. There's a smaller heatsink halfway up the unit, sort of sitting sideways, the rectangle. That is an FPGA. Think of it as a custom ASIC. It's a custom chip that does stuff. And I'm going to talk about that chip. That chip is an important part of the overall hardware enforced remote access solution. So keep that in mind. The hardware is physically able to send information only one way. The left-hand circuit board has a transmitter, a laser, not a transceiver, an optical transmitter. The right hand has an optical receiver, not a transceiver, a receiver. And on the front panel, there's a short piece of fiber, usually exactly 18 inches long, orange fiber, that connects the two circuit boards. And it lets you send information from the wind farm, from the solar farm, out to the world. It lets nothing get back. There is no laser in the receiving circuit board. I mean, think about it. With a firewall, you might imagine that, look, if the firewall is configured correctly and it's fully patched, then it should not allow attacks to get into the OT network. With this hardware, it does not matter how the software is configured. It does not matter whether it's fully patched. The hardware physically cannot allow attack information to pivot into the OT network. So that's, the hardware. The software in the normal gateway, just for the record, you might ask, how does this work? The software makes copies of things. The software is a client of a Pi database, a historian database, an Oracle database, an OPC server. It's a client of a data source on the wind farm side. It gets all of the latest data out of that source. It pushes the data through the strange one-way hardware. Nothing else in the world sees that strange hardware. It's just the gateway software sees that hardware. And on the other side, it's also a client on the IT side. It logs into an identical server, Oracle, Pi, the historian, whatever, and inserts the data. And now you've synchronized these two data sources real time. On the IT network, anyone who needs the data asks the copy, the enterprise copy of the enterprise server for the data. They get the same answers as the live server would have given, give or take a few hundred milliseconds. The hardware means it's no longer possible to send questions into the OT network to get the data. The software means it's no longer necessary to send questions in because all of the data that's allowed to be shared with the enterprise is out there on the enterprise network already. And, in a sense, it's no accident that Hera uses the gateway. Lior invented both.
Yeah, first of all, it's exciting to see how all of these technologies are growing and expanding and becoming reality. When we founded Waterfall, the company, based on the unidirectional gateway invention, to replace perimeter firewalls in OT networks, because these firewalls are being hacked day in and day out. There's no single attack that we've documented ever that was successful without somebody getting in through the perimeter firewall. I mean, if the firewalls were effective, these attacks would not have happened. It's different when you're thinking about two IT networks between between an enterprise network and the internet. There's a different set of risks and ways to overcome them. When one side is OT, one side controls physical processes, and the other one is the internet, the other one is an IT network. Firewalls were not designed for that, and they don't really support the security needs. So, invented this technology, built Waterfall around this, and the other supporting products and technologies that we have for various use cases of our customers globally. And now, using this as a foundation technology for Hera is super exciting. We have a lot of insight and experience in the market, and got a lot of feedback and requests from customers asking about solution that can support their needs because of all of the risk that we talked about remote access in this session already. Let's move forward. I'm guessing from all the questions I see here in the webinar, everybody is excited to see what's coming up.
So let's finish the job here. Hardware force remote access is a technology that's built on top of two cooperating unidirectional gateways. One gateway sends screen images out, and the other one sends encrypted keystroke and mouse in. Otherwise, the architecture is very familiar. We got a remote laptop, just like in the software remote access. We got the intervening network in this example, the internet. You've got the access server in this example, the Hera gateway, and then of course we got the target that we're protecting. Two gateways, screens images out, keyboard and mouse in. You might ask, well, why is that any different than the software? Doesn't the software do that as well? Well, let's look at the attack scenario. Let's compare attack scenario. So we're just going to take the one attack scenario. We don't have time for more than that. But if you recall, the scenario was, watch for a vendor security update. Oh, look, there's a vendor security update. Has it been applied? Or, worse, find a 0-day. But again, you've got a fixed IP address, hasn't been applied yet. Take over the internet-facing CPUs. Now, remember, there's two CPUs in each of these devices, one on the inside, one on the outside. So there's 4 CPUs in the 2 devices together. Imagine the bad guys have, got in before the patch could get in, and they take over both of the internet-facing CPUs on the Hera device. Okay, both of the CPUs right here. I hope you can see my mouse. Now, what do? Well, what they want to do is pivot into the OT network. So the lower CPU, the outbound CPU, they're going to try and launch attacks through the hardware back into the OT network, and it doesn't work. Why? Well, because the hardware is pointing the wrong way. Nothing can get back into the OT network. That's fine, say the attackers. We got the other CPU too. And so they take the top CPU, the inbound CPU, and they launch, SYN floods, and they launch buffer overflows, and they've stolen passwords. They send remote desktop, sessions in there with the stolen passwords, and the hardware throws them all out. What? The hardware throws them all out. Remember that ASIC? The hardware, the hardware on the lower device is normal. It lets screen images and, if you want, other data out. The hardware on the upper device will let encrypted keystroke and mouse in. That's it. It throws everything else out. Fine, say the bad guys. what we have to do then, we have to do this the hard way. We're going to intercept, we've got both these CPUs under our thumb. We're going to intercept the screen images. We're going to fake the keystroke and mouse. We're going to use the faked keystroke and mouse to take over the inside CPU on the Hera device. And from there, we're going to pivot into the OT network and work our will upon the physical process. Well, here's the thing. The credentials, what's happening across the internet is a normal TLS connection. It's encrypted. But if you take over the endpoint of a TLS connection, you can look inside it. Right. What do you see when you look inside? You see encrypted keystroke and mouse. Okay. How do you fake? Where are the credentials for that encryption? That encrypted, those credentials are stored in a TPM module. This is a hardware module that's built into all modern CPUs. If you've got a Windows 11 capable CPU, you've got a TPM built into it. It's designed to keep those credentials out of memory so they can't be stolen. So, the Hera software encrypts using those credentials, and it decrypts in the TPM module on the inside CPU. So in order to break into, they got to steal these credentials. In order to break into the inside CPU, to steal the credentials, they first have to break into the inside CPU so they can steal the credentials, but they need the credentials to break into. It's a chicken and egg problem that we've designed, that Lior's designed into the problem. It's, having taken over the internet-facing CPUs, the attacker has gained no material advantage in terms of breaking into the OT network. It's dramatically more secure than a software solution.
Yeah, Andrew, I think the magic in this technology, in the Hera technology, is that it provides a full-blown interactive remote access, a remote desktop style of experience, of user experience. But under the hood, it's a totally different technology, providing real security while allowing full remote access. I think the three main issues, if you want to look at it from a different perspective, the three main issues with all of the remote access solutions out there. First, we touched already, it requires a firewall at the OT perimeter. Once you have that, you're toast. It's just a matter of time. Somebody will get in through that firewall. That's how it works. The second thing is all of the protocol used by remote access solutions, really good solutions, top of the notch, all of their underlying technologies like the Windows RDP and the rest are super complex. Okay, in this case, even the residual security that a firewall can provide, filtering the protocol that goes in and out through the open ports, doesn't work here. These protocols are so complex. The ports that you open through that firewall are just, allows anything to get in and out. They can't filter, they can't add any meaningful security for that. And the third one is it's too easy to steal credentials of the users, to run a man in the middle or a session hijacking. And with Hera, we solved all of these. Okay, we solved all of these problems. There's no firewalls at the perimeter, as you just described. Our protocol, the Hera internal protocol, is super simple. We are sending in a carrier protocol. We're sending key strikes and mouse moves and sending back a stream of a video of your screen. Filter it to whatever level you want. And the fact that we're using a TPM we're requiring a TPM on the client host, and there's a embedded TPM on the internal side of the inbound Hera gateway. And in the onboarding of the user, there is a key exchange process, means that there's in a sense, a hardware enforced cryptographic coupling between the user, the host, and the waterfall gateway. Meaning that even if I steal your credentials, it's the encryption keys on both sides are kept inside the secure enclave of the TPM. And running a man in the middle here is super, super complex. I don't want to say it's impossible, but if that's the bar, we are really good. Okay, we are at a totally different posture compared to any other technology in the market.
That's right. And I advanced the slide here because you were basically, explaining what's on the slide here. Hardware enforced protocol break, dual encryption, TPM,
Did I take your part? I'm sorry.
enabled. Sorry?
Did
Yeah,
I
no,
take
it's all
your
good.
part?
Sorry,
No, go. Sorry.
go. Okay. Dual encryption to prevent, the forged keystroke and mouse. The protocol complexity is the enemy of security. The more complex something is, the more holes it has. The protocol is simple. It's designed to be simple. It's designed to be hardware filtered, and we are leveraging the TPM security, the best practice modern security to the max. Again, a different kind of hardware enforced security. Real quickly, the user experience will seem very familiar to anybody who's done any kind of remote access. There is a client. We don't use web browsers. They're too easy to steal the cookies, to steal the sessions. We use our own client. There's a client installed on the laptop, my laptop in the hotel room, if you remember. When I bring it up, it says you're allowed to connect into these Hera devices, these sites, those companies. I've got 17 of them. Which one do you want to connect to? So you pick one and you connect. And then it shows you a different screen because now I'm talking to the inside CPU on the Hera gateway, on one of the Hera gateways I'm allowed to connect to. And it says, okay, there are 7,000 devices in this, 300 turbine wind farm. You're allowed to connect to 4 of them. These are your 4 devices. What do you want to connect to? This is the zero trust piece of it. It's not a VPN. You don't get to connect to all 6,000 devices with whatever protocol you want. So I want remote desktop into one of the parts of the SCADA system. You click on that, and it brings up the little HMI that's part of the control system. And now you're moving the mouse, you're clicking on things, and it's interacting as if it were a remote desktop session. But understand, it's the Hera protocol coming across the internet. It's the keystroke and mouse going into the system, and it's remote desktop from the Hera device into the OT network. We're using the protocols the OT network understands on the OT side, and we're using something much stronger on the internet-based side. So let me go through real quick. We've talked about security all the way through here. If you're curious, there's also features, all of the usual features. There's session recording. People say, oh, isn't that intrusive? No, as a remote vendor, I want my sessions recorded. Why? Because the last time, anytime something breaks in the wind farm, who's the finger pointed at? It's pointed at the vendor, me, who logged in last. It must be my fault. I broke it. I want to go to the recording and say, no, here's what I did. None of that would have caused the symptom you just saw. I'm off the hook. So recording there is for the benefit of the owner and operator, as well as the benefit of the remote vendor. There is optional session supervision. So you might trust me, Andrew, to log into my 4 computers, when I need to, but you might not trust me completely. I might in training. And so when I try to connect, it gives me a message saying, please wait. And it gives an administrator an alarm saying, Andrew's trying to connect. Do you want to let him in? And the administrator says, yeah, let him in. But show me what he's doing. And the administrator can watch me and say, no, he's not supposed to be doing that. Click disconnect Andrew. And the next message pops up and says, you just disconnected Andrew. Would you like to disable his account? Yes, disable his account. He needs to go back to training. So these are all standard features. There's integration with the SEMs and with the security operations centers. There's detailed logging. The compliance people look at this and drool because there's such detail in the logging. They, makes their lives easier. There's multi-factor authentication support. There's multi-site management tools. There's the zero trust controls. You can't connect to anything. You connect to the machines you're allowed to connect to. That's it. There are the obvious. You got to be able to provision new users. You got to be able to delete new users or old users over time. And the whole thing is designed for industrial. There is technology under the hood. You don't really see it, but everything feels responsive. And you're going, but I'm going halfway across the world and back. Yeah, but it's designed for high latency, low bandwidth communications and still makes it all feel local and interactive. So it's not just security. The technology is mature in the sense that it has all the features you expect. That's what I had for you. A word about Waterfall. We've been in business almost 20 years. Lior founded the company. We have offices in 6 countries. We're installed all over the world. And we're trusted essentially by heavy industry and critical industrial infrastructure all over the world. So let me wrap up. Renewables are the future of power generation in many jurisdictions. In Europe, in North America, practically all of the new build for power generation is renewables. Remote access is intrinsic to renewables. It's the nature of renewables. It has to be there. And hardware enforced remote access is what the authorities are recommending. It's what I'm recommending as the future of secure remote access, not software remote access anymore. This is secure remote access. This is remote access that is secure enough to stand up in the face of even sophisticated attacks. That's what I had for you. Lior, did you want to chime in?
I think you did a great job, Andrew.
Okay, carry on then. Do we have questions? Natalia, how's the queue looking?
It's looking great. Thank you, Andrew. Thank you, Lior. Great presentation. We've got quite a few questions. Our first question: Have there been real-world examples of the inverters being damaged from cyber attacks?
I track this stuff I'm one of the co-authors of the Waterfall Annual Threat Report. And no, I have not seen any report of the destruction of inverters based on a cyber attack. I do know that a number of authorities are looking at this. And there are designs for inverters that are more robust, but especially grid scale inverters, it's one thing to consumer devices have to be, I'm sorry, idiot proof. Why? I'm a consumer. At home, I'm an idiot. This is the nature. So to answer the question, no, there have not yet been fires due to inverter compromise, but it is something that a lot of people are worried about. And, this is something that owners and operators have to do something about, not just worry about when we have large installations that are at risk this way. And for the record, these inverters are used not just in solar, they're also used in wind. Not all, but a very large fraction of the existing wind inventory produces direct current and has this risk with inverters, as well as the risk of physically destroying the turbines by orienting them into a strong wind the wrong way.
And Andrew, I think we should treat this as an example. Okay, I mean there are many subsystems and modules and products inside a control network, inside a renewable control network. It doesn't matter what type of renewables. They have batteries, they have the turbines, they have safety systems, and with a remote access solution, with a remote access capability, sorry, a bad actor can shut down the operation or threat to shut down the operation, as you know, for a ransomware, or really shut it down if it's a terror attack or something like that. They can misconfigure the network. They can misconfigure a variety of basic capabilities there, and create damage. So I think we shouldn't. I mean, this was an example to show the relevance of the threat, but at the end, allowing somebody log in to a computer that is part of that network from remote opens up all of these risks. And I'm sure we all agree on that. I mean, this is like a basic threat that comes from remote access.
Thank you. Second question. Adding cybersecurity can impact the timing of receiving information. Are there concerns around adding these features that could impact the quality?
Generally speaking, not. We're talking remote access. You know, we're using, I mean, nowadays everybody uses Teams, everybody uses Zoom. From time to time, I mean, anybody who's involved in remote support, providing support to other people, PC help desk, you know, my mother on the, you know, 3 hours drive away has trouble with her computer and says, Andrew, can you help? I remote into the computer and I help. When I remote into the computer 3 hours drive away and I move the mouse, it's a little sluggish. We're talking remote access. We're talking people operating these things. People don't operate on millisecond timescales. Okay, human reaction time, give or take, is 1/10 of a second. Mine is worse than that. This is why I don't play some sports, because I get trounced. I have terrible reaction time. But we're talking, you know, 1/10 of a second. We're talking 100 to 150 milliseconds, and that's that's as fast as you can react. Realistically, you don't react that fast to every stimulus. You have to think about it for a moment. This is, you know, as long as you don't have to move the mouse and wait 20 seconds for the screen to update, you know, it just works. And again, this technology, this product is designed for industrial environments where there is a little extra latency. We've heard no complaints whatsoever about the responsiveness. It was designed to be responsive.
And another data point is remote access, especially into remote site over the internet, regardless of the technology, has delays based on the internet and the, you know, so you are assuming that there might be lagging or connectivity issues. Some of these sites are using you know, cellular communication to get into the network, and some of them are using satellite links. So it's all, I mean, at least our technology doesn't add anything meaningful on top of that.
That's right. And it's not like this is a VPN either. With VPNs, you might have, I don't know, a logic control loop on your laptop that's talking Modbus to a PLC and trying to remote control the PLC. Well, you can't do that with Hera. That's a bad idea security-wise. Remember the malware jumping through the VPN scenario. If you need that kind of capability, if you need that kind of control loop to help debug a problem, that needs to exist in the OT network on an engineering workstation, on a diagnostic workstation, on your workstation inside the network if you're there often enough. And then it's local. It has local access to the local network. It's the human part that is being remoted, not the machine decision making.
Thank you both. Next question. What are your thoughts on implementing moving target defense to randomize the IP address of the inverter of the laptop with the RSA?
So I don't know if you're familiar with the term, Lior. Moving target is it's a cloud-based thing cooperating with your local. What you connect to for the remote access is a cloud address that changes from time to time, and your software can figure out which is the right one. And it's an extra layer of defense. I will argue that it is complementary to HERA. I don't know that we support it now, but it's something that could be added on top of HERA, so to not only make it hardware enforced, but make it harder to find in the first place. How much security would that add? We'd have to look at attack scenarios and ask which attack scenarios are defeated in one scenario versus the other. But I don't see it as a competitive technology. I see it as a potentially complementary one.
Thank you. Well, we approached the top of the hour, but let's maybe take a couple of more questions. How common is it for utility scale solar or wind to be internet exposed? Isn't that much more common for commercial or residential scale?
So I'll take that, Andrew. You can jump in afterwards. So I'll say that I'm happy to say that it is as a CEO of a company getting paid for these types of systems. I'm happy to say that this is very common. As a citizen of a country that being in countries where this is the case, I'm saying unfortunately it's the case. But you would be surprised to understand that the majority of the networks in these types of environments are either directly or indirectly accessible from the internet. There are many reasons for that. I don't think we have the time to go into all of this, but if you'd like, we can take this offline. There are many reasons why we got to this situation, but the majority, even in critical infrastructure of control networks today, are accessible, again, directly or indirectly to the internet.
Right. So I would just add a terminology thing there. In the terminology I was using through the presentation, I would sort of say the same thing by saying in the vast majority of OT networks, there is a pivoting path from the internet through intervening networks like IT networks into the OT networks, all the way down, most often into protective relay networks, which prevent damage to equipment, and too often into safety instrumented systems. So yes, the existence of a pivoting path is nearly universal. One of the big exceptions is everything that uses a unidirectional gateway has broken the pivoting path. But it's, if you've got a 20 megawatt wind farm or solar farm, there's almost certainly a pivoting path into it.
Thank you. And let's take one more last question. Has this type of security protocol implemented in the natural gas industry?
Yeah, this is a great question. It's almost so good that I thought maybe we planted it, but the first HERA customer earlier this year is a natural gas facility. So short answer is yes.
Yeah, longer answer is they have rules and regulations as well. They don't have NERC-CIP, they have different rules. And this class of remote access is very compatible with those rules. Those rules have everybody thinking about their perimeter, have everyone thinking about pivoting paths. You don't have to explain the problem to that industry. They know what the problem is. They see the solution and go, well, let's talk. And so good things are happening.
Thank you both. Well, I guess that's it for today. Andrew, Leo, any last word?
I just want to say, thank you to everyone joining us. Thank you, Leo, for joining us. And, there's something new in the world. There's software remote access. There's the unidirectional stuff that's one way out, nothing back. There's something new in the world that is hardware enforced. It's stronger than software. It's between these two extremes. And it feels like normal remote access. It's, again, it's something that a lot of people in the industry are getting excited about.
Yeah, thank you, Natalia, for making this happen, and Andrew for having me here, and all of you guys that join and listen. And we'll be happy to take any more questions or anything. You can reach out to us, and all the rest of the questions that we haven't answered here, we'll contact you directly. And have a good rest of the day and the week.